Hello, welcome to another lesson of sectoral structures theory. Today we will start going into the real combinatoric nature of this theory and a little bit away from the geometry and trigonometry. We will define today what a sectoral sequence is, not a sectoral structure yet, but a sectoral sequence. We will show this example here. We have this sectoral sequence over here made of a number of sectors. It starts with A, B. So A and B are two continuous sectors joined by an alpha joint. So A and B are continuous. And then we have a beta joint, so B and C are alternating, and then we have C, D, E all joined by alpha joints, so they are continuous, and a beta joint and another sector. So now we have the alpha joints and the beta joints together creating this sectoral sequence. These two ends here, we will refer to them as delta joints. We will use this delta symbol here. And we will try to distinguish the two of them so that in the future it becomes easier to understand which of the delta joints we are talking about. Let's look at the last or the ends of the sectoral sequence. We have F here forms a single part made of one sector, and we have AB forming a part made of two sectors. Since this is larger, we will refer to this as L prime. So this delta joint here we will call L prime. And this, since this part is smaller, we will call this S for small, S prime. So these two delta joints are L prime and S prime. And we will, in standard form, we will read the sequence from the L prime to the S prime joint. So let's begin. We have this sectoral sequence here. A continuous with B, alternating with C, continuous with D, continuous with E, alternating with F. Alternatively, we know that we can replace each continuous symbol with an alpha and each alternating symbol with a beta. So another way to read this, we can say A alpha B, beta C, alpha D, alpha E, beta F. And when we write it in this form, we will call this the geometric form when we name each individual sector. Now, alternatively, what we can do is we can substitute each letter with the number 1. We will refer to this as the expanded form, and later on we'll see why we call it that. So we can say 1 alpha 1, or 1 continuous with 1, alternating 1, continuous 1, continuous 1, alternating 1. So all we did was place a 1 in the place of each sector. Now what we do if we want to abbreviate this into the numeric form, which is what we will use to study sectoral sequences throughout this book, is the numeric form. And here we can see why number theory will creep into this book. When we say 1 is continuous with 1, we're going to add the 2. So we say 1 plus 1 is 2. And then wherever it says alternating, or wherever there's a beta joint, we're going to place a comma. And then we have 1 continuous with 1, continuous with 1. So that's 3 ones. We'll just say 3. And then there's an alternating or a beta, we'll place a comma. And then we have a 1. So we have our first sectoral sequence written as 2, 3, 1. And we will see later on that there's more to this, but this is where we're going to start. So we will say we have this sectoral sequence S. This is a capital S to distinguish from this smaller s. So S is equal to 2, 3, 1. How many parts are in this sectoral sequence? Here it's very easy to see. There are 3 parts. Alternatively, we have 2 beta joints, so we add 1 to the number of beta joints and it gives us 3. So it has 3 parts. We will call the number of parts within a sectoral sequence as the order of the sectoral sequence, and we will use the Greek letter lambda or capital lambda to indicate the order of the sectoral sequence. So the order of this sectoral sequence is 3. Notice also that the order or lambda is equal to beta plus 1. And this is going to be useful again later on. So if we know the number of beta joints, we add 1 and we get the order of the sectoral structure. Now just to recap, we now have 3 types of joints. We have alpha, which are continuous, beta, which are alternating, and we have the delta joints, which are at the end. So we have 3 types of joints. A few more definitions that are going to be very important in this framework. The degree of a sectoral sequence. So remember that any sectoral sequence is made of congruent sectors. So the degree of each sector is the same, and it is the same as the degree of the sectoral sequence. So in other words, if we recall, if we have a sector here, the degree of this sector, and we'll do a reminder what that means, is the same as the degree of the sectoral sequence. And we said that the degree of a sector is basically the number of sectors needed to form a full circle. So if we know the central angle of this sector, we say 2 pi divided by the central angle, and this gives us n, or the degree of the sector, and it also gives us the degree of the sectoral sequence, and this must always be a natural number, otherwise it's not a proper sectoral sequence. Second, we have the magnitude of the sectoral sequence, m, which is simply the number of sectors in the sequence. So 1, 2, 3, 4, 5, 6. In this case, we have 6 sectors, so the magnitude is 6. And this is, of course, always a natural number as well. Now, this will become important later on to distinguish between degree and magnitude. Now, finally, we have the measure of a sectoral structure. We will use the Greek letter mu, and the measure is m divided by n, which is the magnitude of the sequence divided by the degree of the sequence. Let's define one more thing. So we said that the standard form of a sectoral sequence, we can sometimes indicate it with a plus sign, is the sequence from the L prime end to the S prime end. So the large part to the small part. The reverse of a sectoral sequence is indicated by a negative sign, so S negative, and it is read from the S prime to the L prime side. Now keep in mind that these two, the reverse and the standard, are the same sectoral sequence. This is going to be a very core concept to understand the combinatorics of sectoral structures and sequences. So whether I read this from 2 to 1 or from 1 to 2, we're talking about the same sectoral sequence or the same object. However, the way I decide to read it indicates whether it's a standard form or a reverse form, but they are both the same sectoral sequence. So this is a core rule. So S plus is identical to S negative or S minus. We're going to do a few quick examples or applications to this, to the reverse and the standard form. Let S be a sectoral sequence equal to 3, 2. What is S alpha S, or alternatively we can read this as S continuous with S. So we say 3, 2 continuous with 3, 2. What I do in this case, since it is continuous, is we attach these two sets of sectors and we end up with 3, 5, 2. So we added the 2 and the 3 together and we ended up with a sectoral sequence made of 3 parts. Let's do S continuous with S negative. In this case, we say 3, 2 continuous with the reverse, which is 2, 3, which gives us 3, 2 plus 2 is 4, and then 3. Again, it has 3 parts. But notice it gave us a different result. So even though they are identical objects, the notation matters. Let's do S alternating with S. We will say 3, 2, alternating 3, 2. Alternating, we simply place a comma. So it gives us 3, 2, 3, 2. And it has 4 parts, or it has an order of 4. And then let's try something else. Let's say S negative alternating S positive. So 2, 3, alternating 3, 2. We replace this with a comma. We get 2, 3, 3, 2. Again, it has 4 parts. So now we've seen our first set of operations that we can perform on sectoral sequences simply by choosing what type of joint to indicate between them. And we've seen that we can use the reverse versus the standard form to generate more sectoral sequences. Thank you.